So, friends, good morning and welcome to this lecture session of geomorphology. Today, we are going to start a new topic which is called aeolian process and landforms. So, what is aeolian process? You see, whenever we were talking about weathering, erosion, transportation, something like that. So, there are many agents of weathering and erosion we have discussed. The first and foremost thing was the fluvial process, then the fluvial process means the rivers, the streams, the aeolian process, that means the wind process, the wind activity, then the glacial process, then the gravity for mass wasting. So, these are the agents of weathering and erosion. So, out of which this aeolian process is an important domain within that weathering. And aeolian process as it is involves the wind. So, those areas were prone to weathering by wind, that means they indicate the arid regions, the deserts, the coastal plains, is not it. So, that means those area which are governed by this wind as a major agent of peneplenation, landscape modification, those areas we will deal with. And how this wind is involved in landscape modification, to what extent it will modify the landscapes, that will be discussed in this class. So, here it is important to understand that all other agents, maybe it is glacier, maybe gravity, maybe it is a fluvial or the river, those agents whatever the mass, whatever the material they transport, they remove down direction, that means from upslope to downslope direction. But wind is the unique agent of weathering which may transport the material upslope direction, that means wind can blow material from low to high. So, this is an exception, is not it. So, that is why in this class we will deal in detail how the aeolian process they are responsible for this landscape modification. So, now you see wind is always turbulent. So, that means if it is turbulent, so that means whatever these equations we have designed for a turbulent flow, that must satisfy here, that may be utilized here to understand the air dynamics, the wind dynamics, how the change in this turbulence, the change in the wind blow characteristics, that will affect the erosional processes, that will affect the transportation process of this eroded material from one place to another place. Now, if you confine here in these figures below, here you see this is these buildings are here, this industries and some localities shown in this diagram. Here you see this is the percentage of wind velocity, and you see below or close to this ground we have 32%, 42%, 51%, 70 and 89 and 100%. And in this scale we are increasing the height, in this scale we are increasing the velocity. Similarly, now come to less industrial area or the local area where there are trees and whatever these other localities are there, but that means less height infrastructures or less height objects. Here this 100% of this wind velocity is achieved in this level. So, we come to barren rocks, bare rocks. So, there is no locality, no vegetation like this. So, here 100% is achieved at this level. So, that means I want to say wind velocity at this close to the surface is about to 70%. Here close to the surface is 49%, here close to the surface is 32%. So, that means I want to say the velocity of wind, it increases with less vegetation, less infrastructure, less object. That means, whenever there is a free area, free land mass or free anything which is not forming creating an obstacle to the wind movement, here at lesser height wind gains its maximum velocity. But once more and more objects, more and more heightened objects we are introducing the system, we are gradually restricting the winds to blow, and finally, that is why the maximum velocity of this wind is achieving at higher levels. And in this figure, if you see here, this is relative wind velocity, this scale in this direction. Here close to this surface we have less velocity. Once we are increasing more and more height, this is the height scale. Once we are moving to more and more heights, gradually you see the length of the arrow is increasing. That means, the velocity is increasing. So, that means, if we draw a graph, it will look like this. So, once we are moving more and more heights, that means, we are increasing the wind velocities. And in this particular photograph or particular figure here, if you see, these are the impressions of some sand particles, and wind is allowed to blow on the surface. So, here the surface creep greater than 0.5 mm, 0.7 to 0.5 it is saltation, then it is turbulent eddies, then here suspension 0.02 to 0.07 and long term suspension 0.02 less than 0.02 mm. So, that means, I want to say, once wind is blowing, it is blowing and it is interacting with objects of different size. For example, in this particular case, if you say that we allow the wind to blow on a free sand surface, suppose, because whenever why we are taking sand as an example, because we are talking about this wind activity in the arid region, the deserts like which is full of sand. Suppose it is full of sand and wind is allowed to blow on it. So, finer particles that will move off in the form of suspension, then relatively coarser particle they will move in saltation. Saltation means it will move like this and this like this. So, that like jumping. So, this is saltation, and larger particles they will travel by rolling, rubbing on the surface, that is called creeping. So, these are the characteristics movement of particles with increasing size and increasing wind velocity. So, as we assume and as we know that the wind is turbulent and every equations which is designed for a turbulent flow will be holds good here. So, turbulent flow in water or any other fluid above a thin turbulent layer where the velocity is 0, the velocity clearly increases rapidly, then less rapidly with height. In air, the thickness of the stagnant boundary layer over a flat granular bed is 1/30 of this grain diameter. So, if you see here, so once we say about this turbulent flow, that means we know in turbulent flow there will be a boundary layer, the boundary layer where velocity is 0, and that means this system is stagnant. So, above that the velocity increases very rapidly and then the rate of increase gradually decreases. Similarly, here is say, suppose we are allowing the winds to blow on the mixture of layers or mixture of rocks, or simply for example, for better understanding you say the wind is blowing on this material having equal size diameter, equal grain size diameter. So, this boundary layer, that means there is 0 velocity, that layer from the surface of this grain boundary is equal to 1/30 of this grain diameter. So, if we are allowing the wind to blow on sand, that means this boundary layer is very negligible, very close to this surface of the sand, 1/30 of the grain diameter. But if this much size boulders are there, the wind is blowing. So, that stagnant layer will be 1/30 of this boulder diameter. So, that means larger and larger the size, so larger is the distance, is not it, of that boundary layer. So, here two figures are given, one is on a logarithmic scale and another is a linear scale, and this wind blown velocity of wind of different strength. For example, if you see here for this particular graph, here with less height, it is height, this scale is the height, this side is the velocity. Here with less height, the velocity is maximum or velocity is increasing with less increment of height. So, here wind is of a high strength, because if you feel it near to the surface, close to the surface, you see very that means 0 centimeter or this is 1 centimeter, that means it is 1 millimeter. That means the wind is blowing close to this surface of the earth, very close to the surface earth, with touching with the surface very high speed. That means the wind strength is very, it will create more damage. But here in this particular case, here this wind velocity is increasing, but here this rate of increment is different as compared to different. That means, we are moving more height to achieve the more velocity. Here that means, the wind strength is low. So, that means, similarly this is the same case, it is in logarithmic scale. So, that means, wind strength once we say very close to the surface or the surface of observations, at what extent, what height we are achieving maximum velocity. So, if it is close to the surface, we are achieving maximum velocity, that means, we can say it is a strong wind, strength of this wind is more, or the reverse is true. So, this boundary layers about which we are talking, above that stagnant or the boundary layer, wind velocity is proportional to the logarithm of the height, from which the parameter v or the drag velocity was defined as being proportional to the rate of increase of wind velocity in the logarithm of the height. So, what this velocity or the drag velocity means the velocity at which a particular size of grain will be dragged out. So, that means dragged out from this stagnant system, from this, suppose there are number of grains are lying at particular velocity, a particular grain size that will be dragged out, that will be lifted up. So, this is the drag velocity. So, that velocity is equal to this, it is by represented by this formula root over of tau by rho. This tau is the surface shear stress and rho is the density of air. So, although this velocity v has the dimensions of a velocity, but it is really represent the vertical velocity gradient near to the rough surface. Why vertical velocity gradient? Because whenever you talk about this wind blown material, that means at a particular velocity this material will lift near about vertical. That is why it is called this vertical velocity. Although v has the dimensions of this velocity, it really represents the vertical velocity gradient near to the rough surface. When it exceeds the threshold level, that threshold level is v t equal to the vertical settling velocity of a particle. That means, this sand grain or any grain that will lift near about vertical. So, once it moves up, once it moves to the system, it will try to move and remain in this air, but that depends upon this wind blown velocity as well as this density as well as the grain size diameter of this system. So, here the pioneering work by this gentleman Bagnold 1941, it demonstrated that the threshold velocity is proportional to the square root of grain diameter of grains larger than about 0.1 mm. So, this formula or this assumption is right or it is validates for those grains having diameter more than this 0.1 mm, but those grains which are less than that, it is not holding good. Why? Because we know, if you analyze, if you can recollect, when there is a grain size variation in a fluid system also, the larger grains can be transported with relatively less velocity and can be lifted off with from this river bed with less velocity, but those smaller grains like clay, silts, we need more velocity of water to lift it up. The same thing is here applied. So, that means those we are talking about this turbulence flow, this wind velocity, the threshold velocity, they all are valid for those grains which are more than of 0.1 mm diameter. But those grains which are silt and clay size particles, this equation will be different, and it will different means in the sense I say that means we need more velocity to lift a grain of smaller size from the system as compared to the larger size. So, that means you see subsequently other workers after Bagnold 1941 says that the air in or in water grains smaller than 0.06 mm, that means silt and clay particles are transported primarily in suspension, because the settling velocity is less than the vertical component of turbulence flow. Here it is important thing to understand. Settling velocity, that means a grain is settling either it is air or in water. If you are considering water, then we will consider the water system. If you are considering air, that is free fall in the air, that means talking about the wind system. So, that means larger grain fragments, larger grain size like silt and clay are transported primarily by suspension. Why they are moving in suspension? That means maximum time they remain within this air. Why? Because their settling velocity is less than the vertical component of the turbulent flow. So, the vertical component of the turbulent flow is more as compared to their vertical settling velocity. That is why this component is able to make in suspension. So, in air much of this entrainment of fine particles is caused by impact of larger grains, because we know when there is wind movement, there are different types of movement as we have discussed in a few minutes back. There will be something in the creeping, that means rolling, and something is the saltation and something in the suspension. So, here whatever during saltation, that means by jumping of grains, suppose one grain is here and we allow the wind to pass through it. So, it will move here and will hit this system and will again move there. So, once one grain is coming and hitting the system here, there the free sand grains are there. So, that means it impacts on larger grains. So, these larger grains once it impact here, that means it entrains number of particles. So, that is why those number of particles, if they are smaller their size, so they come to in the suspension mode, because their vertical settling velocity is less than that the turbulent component or the turbulent that the vertical component of the turbulent flow. So, that means that is why more and more number of grains we are putting in suspension mode. So, that means gradually we are increasing the density of the system of the layers. The threshold of erosion is linear for larger grains, but once it comes to this minimum grain size about 0.08 mm in air and about 0.2 mm in water, the threshold velocity for erosion rises steeply. So, in air the fine particles on a flat surface lie entirely within that stagnant boundary layer and are not easily mobilized. Very interesting here to discuss. Suppose we have a flat surface, we are putting a number of grains of different size and we are allowing wind to blow. So, once we are increasing and increasing the wind velocity, at a particular threshold velocity comes when the larger grains will be picked up, because that larger grains which is about that is larger than that threshold, that is minimum, that means 0.1 mm. If those grains which has more than 0.1 mm, that will try to move. However, those grains which are of less than of about this, they will not move. Why? Because they are that means in this air particle, the flat surface, entirely within this stagnant boundary layer, because we know that stagnant boundary layer is 1/30th of this diameter, is not it, 1/30th of the grain diameter. Here we say that there is boundary layer and are not easily mobilized. So, those grains, those fine grains, they comes within that boundary layer and it is not easily picked up by this wind velocity. So, that remain there, that means coarser grain, relatively coarser grain will be removed, but finer grains, for lifting a finer grain we have to increase the wind velocity there. Therefore, the Shield's curve for air is similar to that of water for sand and larger grains, but rises much steeply for the silt and clay size particle. So, that means we have to increase more and more that wind velocity to lift finer grains as compared to the coarser grains. For example, suppose a dry Portland cement powder, it is lying in the floor of the wind tunnel. When this threshold velocity Vt, threshold velocity exceeds 100 centimeter per second, a wind strong enough to move fine pebbles with diameter 4.6 mm. So, that velocity that can move this 4.6 mm diameter grains. However, the same velocity is not able to pick up a Portland cement grain. Why? Because that grain remains within that stagnant layer. So, that means that velocity is not able to pick these Portland cement particles. For sand particles exposed to wind, also there is a lower impact threshold of motion at a velocity less than the fluid threshold, caused by other sand grains already in motion striking particles at the rest. So, that means whenever there is sands are in motion, that sands are putting an impact on these other sand grains, but once this velocity, that means this impacted grains, they also some velocity is added to it, but that velocity is not enough. So, that means still it remains within that boundary layer, that is why it is not picked up. If smaller grains have already been set in motion, their impacts will cause larger grains to move also, but at velocity only about 80% of this threshold velocity predict for the particle grain size here. So, that means either larger grains they are impacting on smaller grains and smaller grains they are impacting on larger grains. So, larger grains impacting on smaller grains, that means they will lift it up. Once they lift it up, they remain in the suspension, and sometimes whatever this larger grains impact on smaller grains on clay and fine particle, but still it is not able to lift it up, because that remains within that threshold velocity, that impact velocity which is gained by these smaller grains, but still it is less than that threshold. So, that is why it will remain within that layer, but smaller grains once it is impacting on larger grains attain some velocity, but that velocity is about 80% less than or 80% of the threshold velocity it is required to lift a grain, that is why that remain stagnant. Because of the great density contrast between the air and rock fragment, only very fine detritus within an effective diameter of less than 0.2 mm and usually less than the minimum size of very fine sand, that means 0.0625 mm, can be maintained in suspension by the upward component of the atmospheric turbulence. So, that means whenever there is atmospheric turbulence, the wind is blowing, a mixture of material is there, only the fine fragments of this much size or so, they will remain on the suspension, and other things that is larger than that, that will be in saltation mode, and larger to that than that, that will be in the creep mode. So, now this is called dust, that means this finer particle, the silt and clay particles which is remain on the suspension mode, this is totally collectively that is called dust. So, this is dust that grades into extremely fine particulate matter called haze, smoke or aerosols, which can be carried entirely around the world by planetary winds before settling out or being washed out by the air. So, here those particles by any means, either due to increase of velocity or by impact of grains, any means it comes to a suspension mode. If this wind velocity remain as it is, they will remain in the suspension mode, and those particles they remain in the travelling conditions. So, that can go up to thousands of kilometers distance. For example, in Narmada Valley, when we are talking about this weathering and erosion and mass transport, you might be remembering. So, in Narmada Valley, we have some that is what is called that volcanic ash beds. So, those volcanic ash bed was dated back to several thousands of years, and the origin was traced in the volcano of Toba. So, that means you see from here to Toba, Indian subcontinent, not only on Indian subcontinent, most part of the Southeast Asia, this area, this volcano from this Toba, the volcanic ash from Toba was distributed. Why? It is thousands of kilometers apart. So, this is because particles, this composed of this silt, the clay, even if not silt, it is clay particle, very minute size. So, once they come in suspension mode, that can travel large distance, thousands of kilometers, remain in the suspension mode, because to settle down the wind has to be calm for a long time. That means, the threshold limit, the threshold of the settling velocity, wind velocity less than the threshold velocity, then it will settle down. But most part of this, if the wind velocity remains above than this, even if slightly above than the threshold velocity, but still this particle will in the suspension mode. That is why those suspended materials, that clay size particles, that is called haze, smoke or aerosols, which can be carried entirely around the world by planetary wind before settling down and being washed out by air or water. So, loose sand particles with a diameter of 0.2 mm or larger can be steered by a steady light wind of 5 meter per second, but do not remain in suspension here. So, for suspension we need very fine particles. Suppose a mixture of grains are there, mixture of particles size, different size of particles are there, we allow to blow this wind about 5 meter per second velocity. That velocity is able to steer these sand grains, but do not remain in suspension. So, that means, it will not come to in the suspension mode. However, it will pick up this sand particle and it is gradually decrease, and it will fall somewhere else. It will transport from one place to another for a short distance of migration. This is called saltation. For example, if you see this figure, you see this salt, the sand grain, it is taking a trajectory motion and it is coming here. This type of motion, jumping from one place to another place, this is called saltation motion. So, they roll or slide along the ground or bounce, transferring momentum to other grains by collision. Here some of them are rolling, the larger particles they are rolling, that means with touching within the ground, they remain within the ground, but some of them they are moving here by jumping. So, this way, so once this movement starts, sand grain movement starts, they transfer momentum to other grains. Here it is going, and suppose it is moving from here to here or here to here, that means it is transferring momentum. Similarly, here it is jumping from here, once it impact here, it is transferring the momentum. So, that means momentum transfer takes place. So, this gentleman Bagnold 1941 made a thorough laboratory and field study of this physics of wind blown sand, and by the ingenious experiments first demonstrated that most sand grain transported by wind do so in short asymmetric trajectories, never far from the ground, that is called saltation. So, this height, it is not very high. So, how much height it will be, that depends upon the size of this grain and depends upon the wind velocity. So, this experiment, laboratory experiment, and field observation says that those trajectory motions, those sands, they are lifted to very less distance from this ground and finally takes a trajectory motion and impacts on the ground itself. So, this type of jumping type of motion of these sand grains, it is called saltation. So, a falling grain strikes one or more grains and makes a visible dimple or crater on the sand surface. For example, if you see here, this grain is going and coming here. So, once it impacts here, for example, here it is creating an impact and it is disturbing number of grains from this side. Although the disturbed particles are scattered in various directions as they rise into the airstream and fall again, they are swept forward because momentum is gained. So, once the momentum is gained, it will carry forward, but the distance at what distance it will move, that depends upon the wind velocity. So, it may distance up to this, it may distance up to this, or maybe very small distance it will migrate, depends on the wind velocity, the size, the density of those grains. So, a lesser amount of sand is driven forward over the ground surface without saltating, called surface creep. So, if you see here, there are three types of movement. One is saltation movement, it is jumping. One is your suspension movement, here suspending material, that is very fine, that is dust or aerosols, whatever may be. Now, very less amount of sand is driven forward over a ground surface without saltating is called surface creep. Here these are the surface creep, that means they move along this ground, they do not leave this ground at all. So, on the surface they roll, they slide or different type of movement. So, this type of movement, it is called creep movement. The effect of increased wind speed is to impart a higher forward velocity to saltating grains, which in turn produces a rapid increase in amount of sand in transport. So, that means more and more velocity we are adding to the wind. So, that means more and more transportation capacity we are increasing, which in turn produces a rapid increase in amount of sand in transport. So, more amount of sand is transported. So, more amount of sand is transporting, that means the landforms which are going to form, it will be more, it will be larger landforms. So, that means the landforms is proportional to deposition. So, whenever more and more sand we are introducing in a system, that means we are creating a deposition landform of larger size. Most of the sand saltating over a surface of similar size grain does not rise higher than 1 to 2 meter regardless of wind speed. Because of this logarithmic decrease in wind velocity close to ground, this median height of these trajectories of all saltating sand grain is only about 1 centimeter above the ground. So, that means it is not much distance it is going. This height does not rise 1 to 2 meter, and similarly it is, if you see here, the median height of these trajectories of saltating sand grains only about 1 centimeter above the ground. It is not going very high from this ground, it is within then 1 centimeter this trajectory height is remain there, and the distance is about 1 to 2 meters. The impact of saltating sand grains can move a much larger grain forward by surface creep. This is important. The impact of a saltating sand grain can move a much larger grain forwarded by the surface creep. You see, surface creep, suppose a surface creep for a particular wind velocity, this grain is under surface creep and it is moving from here to here. And but if it is impacting here, suppose a saltating grain is impacting here, this may move to a larger distance. So, here it is said the impact of a saltating sand grain can move a much larger grain forwarded by the surface creep. So, that means a larger grain more than this can be moved through surface creep, but the distance of movement may be less. So, that means the effect of saltation is more as compared to the effect of creeping. So, that is why these landforms are readily modified in the arid region, mostly due to these saltation processes. So, Bagnold estimated that significant creep occurs in grains 6 times the diameter of saltating grains. However, creeping grains move only few millimeters with each impact, whereas saltating grains have characteristic trajectories a meter or more than in length. So, creeping, though it is effective, but it is up to very few millimeters, but saltating grains it is moving up to meters, and they are in the advanced form in the landscape modifications. So, here this is a potent method of size sorting in which size fraction is differentiated. So, for example, suppose we have sand grains, we have mixture of grains and we are allowing the wind to move. So, in that case sand grains are coming and hitting the system. That is why once they are hitting with larger grains, they impacting on that, but themselves they are separated from the system. So, that means at one part of this area that will be enriched in larger grains, at one part of this area they will enriched in the smaller, relatively smaller grains. So, that is why there will be sorting differences. So, there will be a natural sorting occurs within that. That is why these wind blown materials they are highly sorted as compared to these fluvial systems. So, I think we should stop here, and in the next class we will continue the discussion. Thank you very much. Thank you for your attention.